Alright, so here's some things that you have missed. So atomic number is the total number of protons in an atom. Now if we look at the periodic table, we have a lot of information on here, and the whole number that's inside every box for every element, that is the atomic number. So atomic number for boron would be 5. The atomic number for gallium would be 31. The atomic number for ruthenium would be 44. Another number that we're going to be using a lot is this mass number. Mass number is total number of protons and neutrons in an atom. So if we're given an atom of carbon, so right here we have two of them, carbon 12 and carbon 13. The 12 and the 13, that is the mass number. Okay, so figuring out how many protons, neutrons, and electrons we have. Well, if we look to see where carbon's at on the periodic table, carbon is number 6. That 6 is telling us that it has 6 protons. Every carbon atom has 6 protons. So for carbon 13, we put a 6. Figuring out how many neutrons. Well, if the mass number is the total number of protons and neutrons in an atom, we have that, and we know how many protons there are. If we take the difference between these two, so 12 minus 6 would give us 6. Carbon 13, 13 minus 6 would give us 7. Now to figure out how many electrons we have in each one, we need to know this little bit of information. Atoms are electrically neutral. And the only two subatomic particles that have a charge to them are protons and electrons. So protons, since if we have 6 of them, that means that we're going to have 6 electrons to make this electrically neutral. Same thing with carbon 13. We have 6 protons, we're going to have 6 electrons. These two carbon atoms, carbon 12 and carbon 13, are called isotopes. Isotopes are atoms with the same number of protons but a different number of neutrons. So if we kind of look right here, here's another way that we can show an isotope. We use the symbol and we use these two numbers. The top number is the mass number. Bottom number is the atomic number. So if we look at this oxygen 16 atom, how many protons? Well, atomic number is 8, so it has to have 8 protons. Neutrons, well, mass number minus atomic number, 16 minus 8, 8 neutrons. How many electrons? Well, if we have 8 protons, we have to have 8 electrons for this atom. If we look at this hydrogen 1 atom, well, protons, and the bottom number is the atomic number, so that's telling us that it has 1 proton. Now, how many neutrons? Well, if we take the mass number minus the atomic number, so 1 minus 1, in this case we have 0 neutrons. Electrons, well, if we have 1 proton, we have to have 1 electron. Another number that we use quite a bit on the periodic table, if you look at this one, it's going to be this red number right up here above the symbol. That's called the atomic mass. How do we calculate out the mass? Well, we have problems like this, because with each isotope of an element, it has its respective mass, and it also has its percent of nature. So if we look at this this one example, find the average atomic mass for chlorine. Okay, well, chlorine has 2 naturally occurring isotopes. It has chlorine 35 and chlorine 37. The mass of each one. So chlorine 35's mass is 34.969 AMU, and I'll explain what AMU stands for here in a little bit. And chlorine 36, its mass is 36.966 AMU. Percent of nature, chlorine 35 is, we find it 75.78% of the time nature, and chlorine 37, we find it 24.22% of the time nature. So the way that we find the average atomic mass is we do this. With each of the isotopes, we're going to take its mass, we're going to multiply by its percent of nature. Okay, so 34.969 times 75.78. Excuse that line right there. Accidentally bumped myself. So we're going to multiply those two numbers. Plus, then for chlorine 37, do the same thing. 36.966 AMU times 24.22. Once we do that for each isotope, take the mass times its percent, and that add up all those different isotopes. The last step in the process is we need to divide by 100. Okay, if you want to put it in the calculator like this, what I would kind of do is put double parentheses at the beginning and double parentheses at the end. Okay. For example, open two parentheses, 34.969 times 75.78 plus, then for chlorine 37, 36.966 times 24.22, double close, and then we're going to divide by 100. Let me get that back into floating. So our answer, 35.45 to 45.453. We can say 35.45 AMU. Okay, now how can we tell if this is going to be correct or not? Well, if we look on the periodic table for chlorine, which is 17, see if I can get that to focus in a little bit. There we go, just move in a little bit. Its atomic mass is 35.453. Okay. Now, we are going to do some dimensional analysis with this chapter and everything, and a lot of students think that this kind of dimensional analysis is a whole lot easier because every conversion factor is going to have the same thing. It's going to have this thing called a mole. Now what the mole is the amount of substance containing the same number of chemical units, atoms, molecules, particles, etc., as exactly 12 grams of carbon-12. Okay, that's pretty wordy. Or another way that we can say what the mole is, it is the common conversion factor in chemistry. And the reason why we call it the common conversion factor is because if you kind of look down a little bit, it's equal to a lot of different things. So 1 mole, and the way that we abbreviate the mole is MOL. It's equal to mass of an element, mass of a compound, 6.022 times 10 to the 23rd molecules, atoms, particles. This number has a couple different units with it, and this number has a proper name. It's called Avogadro's number. He's a scientist that's in the PowerPoint presentation. If you look at that, he's right around 1811 is where you see him at. And it's also equal to 22.4 liters of gas at STP. Now what does STP stand for? It stands for standard temperature and pressure. So let's kind of look at the first two real quickly, how that works out. So if we look at, let's say phosphorus. Okay, and on the periodic table, phosphorus is number 15. We look at the mass, we have 30.97376. Now if we kind of round to about 2 spots after the decimal, we can say 30.97 grams is equal to 1 mole of phosphorus. Or if we look at oxygen, oxygen's mass is 15.9994. Or if we just round to 2 spots after the decimal, we just round up to an even 16. So 16 grams is equal to 1 mole of oxygen. Okay. Now let's look at the second one, mass of a compound. So a compound is composed of 2 more elements. So we have a couple examples right here, and let's figure out the mass. And we'll start off with some simple ones. So H2O, and the easiest way to figure out mass of a compound, break it up into the individual elements. Now, with compounds, we're going to have numbers sometimes behind after the elements symbol. That goes with the preceding symbol. So in this first case, we have 2 H's or 2 hydrogens, and we have 1 oxygen. After we determine how many we have of each element are in the compound, the next step is to multiply by that element's respective mass. On the periodic table, hydrogen's mass is 1.00794, so we can just say 1.01 gram. So 2 times 1.01, 2.02 grams. Oxygen, like we had up there, up top, 16. So 1 times 16, 16. And after we've done that for each element within the compound, we add up those numbers. So 2.02 plus 16, 18.02 grams is equal to 1 mole of H2O, water. Okay, now let's look at our next one, NH3. I'm going to move down here just because of space issues. So we have nitrogen and we have hydrogen. Looking at the formula, we have 1 nitrogen and we have 3 hydrogens. Mass of nitrogen is 14.01 grams. So 1 times 14, 14.01. 3 times 1.01, 3.03. Add our 2 numbers up. We come up with 17.04 grams. That's equal to 1 mole of NH3. Sometimes the chemical formula of the compound might have parentheses, like what we have right here. And it will have a number after it. And what we do when we figure out how many atoms of each element there are, so in this one we have copper, we have nitrogen, and we have oxygen. Copper is not inside the parentheses, and it doesn't have any number on the outside of it, so that's just telling us that we have 1 copper. Pardon my use, they kind of look weird. Now nitrogen, inside the parentheses we have 1 nitrogen. Going to multiply that by 2, so 1 times 2, 2 nitrogen, and for oxygen, 3 times 2, 6. Alright, so the mass of copper, 63.55 grams. So 1 times 63.55, 63.55. Nitrogen, 14.01, so 2 times 14.01, 28.02 grams. And oxygen, 6 times 16 grams, 96. We're going to add all 3 of these numbers up. 63.55 plus 28.02 plus 96. Come up with a mass of 187.57 grams. 1 mole of CuNO3, 2. Now this last one, we have aluminum, sulfur, and oxygen. Looking at our chemical formula, we have a 2 after aluminum, so we have 2 atoms. Sulfur, we have 1 inside the parentheses, so 1 times 3, 3. Oxygen, 4 times 3, 12. Mass of aluminum, 26.98 grams. So 2 times 26.98, 53.96 grams. Now sulfur is 32.065, so we'll just take it as 32.07 grams. 3 times 32.07, 96.21 grams. And oxygen, 12 times 16, 12 times 16, 192 even. And we add all 3 of those numbers up, 53.96 plus 96.21 plus 192. Coming up with 342.17 grams. Once again, that's equal to 1 mole Al2 SO4 3. So let's look at some dimensional analysis, and on this side what we're going to be doing is we're going to be doing one-step mole conversion problems. The reason why they're called one-step is because we're going from a unit to moles, or we're going from moles to a unit, and I have a couple examples to show that for you. Alright, so our first one, we have 76.05 grams of CO2 to moles. Okay, so for these types of problems, if you see grams anywhere in the problem, that's telling us that we need to find the mass of our substance. Okay, so we're going to need to figure out the mass of carbon dioxide. So we have 1 carbon and 2 oxygen. Mass of carbon, 12.01 grams. So 1 times 12.01, 12.01. Oxygen, 2 times 16, 32. If you add these up, mass of carbon dioxide, or CO2, is equal to 44.01 grams. And that's what that's going to be our conversion factor for this problem. And just like what we did with the last chapter, we start with the number that was given to us, 76.05 grams. And we're going to set up our ratio. Now, since we're trying to go to moles, what we're going to put up in the numerator is the 1 mole. And since we're starting in grams and want to get rid of it, we're going to put the 44.01 grams down the denominator. So grams gets canceled out. So now putting this in the calculator, put 76.05 divided by 44.01. And that is what our number comes out to be. Now, if we were dealing with significant figures, we have 4 significant figures in the number that was given to us, and we have 4 significant figures in our mass. So we should put down 4 significant figures for our answer. So I'm going to put it as 1.728 moles as my answer. Let's look at this next one. So we're converting 8.88 moles of AS, which is arsenic, to grams. So once again, since we have grams, we got to find the mass of our substance, arsenic. This is a pretty easy one because all we have to do is look at the periodic table and find arsenic. There it is right there, and its mass is 74.92. And that's going to be our conversion factor. Okay, start with 8.88 moles. Use our conversion factor since we're going to grams. 74.92 grams over 1 mole. There's our setup. So let's take 8.88 times 74.92, coming up with 665.2896. Now, once again, with significant figures, we have 8.88, which has 3 significant figures. Our mass has 4, so our answer should only have 6 significant figures. So I'm just going to put down 665 grams as my answer. Alright, let's look at our third one. We have 4.11 times 10 to the 24th molecules of SF6 to moles. Alright, so units, we have molecules and we have moles. And if we look back at our notes, 1 mole is equal to 6.022 times 10 to the 23rd molecules. So that's the conversion factor we're going to use for this one. We don't need to find the mass because grams is nowhere in our problem. Alright, so let's set this up. 4.11 times 10 to the 24th molecules. And since we're going to moles, we're going to put the 1 mole up in the numerator. Down in the denominator, we're going to put Avogadro's number. So So that molecules gets canceled out. Alright, so now how do we put this into our calculator? If you have one of these calculators, the way you do it is, I'll put over here to the side. We're going to take 4.11, and there's a function, and the symbol for that function is EE. And it might be right above a button, so if it's right above a button, then you have to hit the second function button, NEE 24. If you have another button, it might be like EXP or times 10 to the n. You just have to look on your calculator, and if you have any questions about that, please let me know. But this is how we kind of punch in a number in scientific notation to our calculator. Then divide by, then we're going to divide by Avogadro's number. So like I said, if you have a Texas Instrument like what I have right here, you hit the EE, or I might have EXP or times 10 to the nth, 23. Alright, so 4.11 second function, and right there it is, EE 24, divide by 6.022 second function, EE 23, and we're coming up with 6.824975091. So we should only have three significant figures, so I'm going to go with 6.82 moles for an answer. Let's look at one more one-step conversion problem. Then we'll go to what are the quote-unquote trickier ones. They are a two-step conversion problem. So we have 12.87 moles of O2 to liters. All right. So since we're looking at liters and O2 is a gas, we're going to use the 1 mole is equal to 22.4 liters of a gas at STP. So 12.87 moles. Set up, since we're going to liters, we're going to put the 22.4 liters up in the numerator over 1 mole. And we're going to find this one and take 12.87 times 22.4. And this is what I'm coming up with for an answer. Now we should only have three significant figures, so I'm just going to put down 288 liters as my answer. Okay, so let's look at a two-step conversion problem. Two-step conversion problem will be going like from grams to liters, molecules to grams, liters to molecules, something like that. And we still use the mole conversions, and we're going to set, the reason why I call it a two-step conversion problem is because we have to use two conversion factors. So in this first one, we're going to convert 150.15 grams of F2 to liters. Okay, so two conversion factors. Since we have grams, that's telling me I need to find the mass of my substance. So I need to find the mass of F2. Now the mass of a fluorine atom is 18.998 grams. So I'm going to take 2 times 19, comes up to be 38 grams. Now, the other thing is, since we have liters, we're going to use 1 mole is equal to 22.4 liters. So here's our two conversion factors. Let's set things up. 150.15 grams. We're going to use that first conversion factor so we can go from grams to moles. So 1 mole over 38 grams. So that grams gets canceled out, and now we are in moles. Then we're going to use the second conversion factor so that we can go to moles into liters. So in our second ratio, we'll have 22.4 liters up top, 1 mole down the bottom. Moles get canceled out. So 150.15 times 22.4, that's all divided by 38. I'm coming up with 88.5 liters That's my answer. Alright, let's look at our second one. We have 7.02 times 10 to the 23rd atoms of carbon to grams. Okay, so once again, two conversion factors. Since we have atoms, the number that we use for that is Avogadro's number. 6.022 times 10 to the 23rd atoms. Now, grams, since we just have carbon, 1 mole is equal to 12.01 grams of carbon. So start with the number that we're given, use that first conversion factor so we get out of atoms going into moles. 1 mole over Avogadro's number. In the second ratio, since we're trying to go to grams, we'll have 12.01 grams over 1 mole. Okay, so once again, putting this into our calculator, 7.02, and then for this calculator, second function, EE23. I'm going to take that times the 12.01 mass of carbon, divide by, then I'm going to put in Avogadro's number, 6.022, second function, EE23. Our answer, 14.00036. So we need to have three significant figures, 14.0 grams. Then our last example, we have 32.56 liters of SO3 to molecules. So our two units, we have liters and we have molecules. Now if you ever see liters, go ahead and think, okay, this is a gas, I'm going to need to use 22.4 liters. Molecules, that's Avogadro's number again, 6.022 times 10 to the 23rd. So those are our two conversion factors, 32.56 liters. Use that first conversion factor, so 1 mole over 22.4, so we cancel out liters. Then we're going to use that second conversion factor so we can get into molecules. So in our ratio, Avogadro's number up top over 1 mole. (32.56) times 6.022 times 10 to the 23rd, divide by 22.4, and I'm going to put down 8.75 times 10 to the 23rd molecules for an answer. Hopefully this kind of helps you out. If you have any questions, please email me and ask me. I'll help you out as soon as I can. Thank you for watching.